All right, welcome. Today, we're going to dive into one of the biggest, most fundamental mysteries in all of chemistry. It's a question that controls, well, pretty much everything, from how our bodies get energy to how we create brand new medicines.
No, seriously, think about it for a second. You can mix two chemicals and get this spectacular reaction, or you can mix two others and get, well, nothing at all. What's the secret? What's the hidden rule that decides whether a reaction is going to happen or just fizzle out?
So for decades, the textbook answer has always been this famous equation, Gibbs free energy. It tells us reactions happen if they release energy, that's enthalpy, or if they increase disorder, which we call entropy. Now it's powerful, and it's definitely correct, but let's be real, it's also super abstract. It doesn't really give you that intuitive feel for what's actually going on with the molecules themselves.
But what if the answer wasn't just in the math? What if we could predict whether a reaction will happen, not just with an equation, but by literally looking at a molecule's physical structure, its shape, its flexibility, its whole architecture? Well, that is exactly what we're going to explore.
You see, for the longest time, we've treated these concepts, energy and entropy, like they're just abstract numbers you plug into a formula. But this new approach suggests something totally different. It says these aren't just numbers, they are direct, physical results of how a molecule is actually built.
So let's really break this down. The old way versus the new way. The old way treats potential energy and entropy as these abstract things you just slot into an equation. But the new way, which comes from some really fascinating work by researcher Jawad Alzeer, sees them as real, tangible properties that come directly from a molecule's physical structure.
Okay, so this basically flips the script on how we think about this stuff. A molecule's structure, its shape, isn't just a simple blueprint. It is the very thing that dictates how much energy it's holding on to and how much freedom it has to move around. In other words, the structure is in charge.
And look, this isn't just some vague concept. The research behind this puts it crystal clear. Potential energy and entropy can be understood just by looking at the physical features of the molecules. And that right there, that insight changes everything.
Okay, so how does this actually work? How can we use this idea? Well, the framework breaks it all down for us into this really handy toolkit. I'm talking about the 3 C's of structure.
All right, first up, constitution. This one's super straightforward. Think of it like a parts list for your molecule. What atoms does it have? How many bonds are holding it together? This basically sets the baseline for the total potential energy that can be stored in its chemical bonds.
Okay, C number 2 is configuration. This is the molecule's rigid 3D blueprint. You know, how its atoms are locked together in space. And if that arrangement is all bunched up and strained, like atoms are being shoved too close together, that strain is literally stored potential energy.
And our third and final C is conformation. This one is my favorite. It's all about a molecule's flexibility, its wiggle room. The more a molecule can twist and turn and rotate around its bonds, the more different shapes it can make. And that freedom, that movement, that's entropy right there. More wiggle equals more entropy. Simple as that.
Okay, so we've got our toolkit, the 3 C's. Let's put it to the test and apply it to some of the most important molecules in biology, the ones that are literally powering our bodies right now.
Here's a great way to think about this. Imagine a really rigid, strained molecule. It's basically a compressed spring, just waiting to pop. That tense structure, that's its configuration, is just packed with potential energy. And because it's so rigid, it can't move much, which means it has very low conformational freedom, and that means low entropy.
And this brings us to ATP, the absolute powerhouse of our cells. Before it reacts, ATP is that compressed spring. It's rigid, it's strained, with all these phosphate groups pushing away from each other. But then, when it reacts with water, boom, the spring is released. The products you get, ADP and phosphate, are way more relaxed and flexible. That means they have lower potential energy and much higher entropy.
So this gives us a brand new, way more intuitive definition for why a reaction happens spontaneously. It's just a molecule changing its shape to a more stable state, either by letting go of stored up energy, or by gaining more freedom to move, or, if it's really lucky, both.
What's really cool is that this idea doesn't just tell us if a reaction is going to happen, it can also help us figure out how it's going to happen, which specific path it's going to take to get from A to B.
Believe it or not, this framework can actually help us predict the exact path a reaction will follow. Let's take a look at a couple of classic organic chemistry reactions. Take the SN1 reaction. You've got this crowded molecule, right? It's easier for it to just fall apart first, which is messy and creates a ton of entropy before it reacts. But then you have the SN2 reaction, where two molecules have to come together perfectly in one smooth step. That requires a lot of order, so entropy has to drop at first. Even the E2 reaction needs the super rigid alignment, which also costs it some entropy. The molecule's shape literally dictates the journey it prefers to take.
So let's really follow the story of that SN1 reaction, step by step. First, a bond breaks. Now that takes energy, so potential energy goes up. But you're going from one thing to two separate things. That's a huge increase in freedom, so entropy just shoots through the roof. Then, in the second step, a new bond forms, bringing things back together. That releases energy and, you guessed it, reduces entropy. The whole thing works because that big jump in entropy in the first step makes it all worthwhile.
So you might be thinking, okay, that's a neat way to understand my OChem homework, but this is so much bigger than that. This way of thinking, looking at structure, has huge implications for how we actually invent and build the molecules of the future. Think about designing new drugs. Instead of just focusing on how tightly a drug binds, chemists can now think about the entropic cost of forcing a flexible molecule to lock into place. Or in catalysis, we can literally build catalysts with shapes that act like a perfect slide, guiding molecules down the easiest, most efficient reaction path. And for learning, for AI, it means we can finally move beyond just memorizing a bunch of rules and start predicting things from the ground up.
And really, that's the bottom line here. When we start to see chemistry through the lens of structure, through constitution, configuration, and conformation, we get real mechanistic insight. We're not just memorizing facts, we're understanding why things happen.
And that leaves us with one last, pretty big question to think about. For so long, chemistry has been all about formulas on a page. But what could we create? What new medicines, new materials could we build if we started designing molecules based on their actual shape, based on their ability to hold energy like a spring or move with freedom? The possibilities are just incredible to think about. That's the real power here. That's the power of rethinking reactivity.